What is osmotic pressure? Osmotic pressure is the amount of pressure required to stop the flow of the solvent across a semi-permeable membrane. So let's go back to that diagram we had here. Now, originally we had equal volumes of water, or equal volumes of the water on one side and the solution on the other side. And as the semi-permeable membrane allowed the water to flow from B to A, from a region of high concentration to low concentration, the height on A side went up. Eventually, what it does is it creates a pressure on this membrane where the solute, or the solvent particles rather, are moving back across this membrane to the B side, and they start moving back from A to B because of high pressure due to the height here. Now remember, when we are studying gas laws, we saw how the mercury would rise up in the long tube through the dish because the tube was evacuated of all the air. But at some point, just the height of the mercury would be enough to balance out the pressure due to the atmosphere, and we call that the atmospheric pressure. 760 millimeter height or 76 centimeter height of mercury was the atmospheric pressure. Similarly here, as the height of this column of water or the solution rises, it creates pressure which is able to balance out the flow of solvent particles from B to A. So at that point we have reached an equilibrium where the number of molecules of B that are moving from B to A is equal to the number of molecules of of the solvent are moving from A to B. That situation happens at a particular pressure, but we can artificially apply that pressure on the A side, thereby preventing any semi-permeable membrane flow that would otherwise happen. So that pressure is called the osmotic pressure, with a symbol given here. This symbol is called pi. It's a Greek alphabet. It can be calculated by taking the product of I times m times r times t. I times m stands for osmolarity. Osmolarity is the molarity of your solute times the number of the particles of solute. For example, if the concentration of sodium chloride in a solution was 1 molar, then since each NaCl breaks up into two parts, Na plus and Cl minus, the value for I would be 2, because that would be the number of moles of particles per mole of solute. And so 2 times 1 mole of solute would give you I equals to 2. So I times m would be 2 molar. And this is very similar to what we did previously using molality. However, in the equation for osmotic pressure, we do not use molality, we rather use molarity. And I times m gives us the osmolarity. We will look at a question on this topic in a few seconds. But then this value times the gas constant times temperature gives us the osmotic pressure, and the temperature, similar to the gas laws, has to be in Kelvin, not in degrees Celsius. Keep that in mind. So here is a problem. First of all, let's find the osmolarity of 5.0 times 10 to the negative 3 molar sodium phosphate. So sodium phosphate, when dissolved in water, being a good electrolyte, dissociates to give 3 NAs and 1 phosphate, and that's 4 particles altogether, 3 of this and 1 of this. So osmolarity then is 5.0 times 10 to the negative 3 moles of sodium phosphate per liter, which is the molarity, times the number of particles we get, which is 4 moles of particles for 1 mole of sodium phosphate. And so osmolarity is 2.0 times 10 to the negative 2 moles of particles per liter. Now that we have the osmolarity, can we find the osmotic pressure of a 5.0 times 10 to the negative 2 molar solution of sodium chloride at 25 degrees Celsius? Well, the definition of osmotic pressure pi equals Im times RT, and so pi would equal to 2 moles of particles for 1 mole of sodium chloride times the molarity times the value of the gas constant R 0.0821 liter atmosphere over Kelvin mole times the temperature in Kelvin, which is equal to 2.4 atmosphere. So what does this value mean, 2.4 atmosphere? It means that if that much pressure was applied to a solution that had a concentration of 5.0 times 10 to the negative 2 molars, then that would prevent any flow due to osmosis through a semi-permeable membrane.